Hi everyone! We continue our study of a linear association, and in this video we're gonna learn how to model linear association. I'd like to remind you that association is called linear if the points of a scatter plot lie close to or on a straight line. Let's use the following example. Here we have bivariate data that measures the mean ticket prices for 50 biggest concerts of a year for certain years after 1995. So each point and the corresponding audit pair represents the number of years since 1995 and the corresponding mean ticket price calculated for 50 biggest concerts of that year. As you can see from the scatter plot, it's impossible for a straight line to contain all those points, but we can think of a line that comes close to most of them. So what line would that be? Well, here's a sketch of that line. And that line represents a linear model or mathematical description of an authentic situation. In this case, it's a mathematical description of the relationship between the mean ticket price for 50 biggest concerts of a year after 1995. And I'd like to emphasize that this line, this linear model, does not have to contain any of the points. What's important is that it has to come close to all of them. Why do we need a linear model? We needed to make predictions and estimations because, as you can see, we only have 1, 2, 3, 4, 5 points in a data set. It means that we know the mean ticket price only for 5 specific years. But what if we want to know the mean ticket price for 50 biggest concerts for other years? Well, that's where the linear model comes handy. Let's see how this works. Let's say we want to use this linear model to estimate the mean ticket price in 2000 and 2010, and also to estimate in which year the mean or average ticket price was $65. And this is how we're gonna do it. We're gonna use the fact that any point on that line can be described by two coordinates, the x-coordinate and the y-coordinate. Well, those coordinates are corresponding to our variables. The x-coordinate will correspond to number of years since 1995, and the y-coordinate of any point on this line will correspond to the mean ticket price. So if we want to estimate the mean ticket price in 2000, first we need to figure out how many years since 1995 have passed. Well, that's 5 years. So that's 5 on the horizontal axis. Now we have to project that to a point on the linear model. That point will have the first coordinate 5, and then check its corresponding y-coordinate. So that is about 42. And that means that the mean ticket price in 2000 was approximately $42. Well, it's important to always say approximately because linear model only estimates and approximates the values. Let's try that for year 2010. First of all, let's determine what number it corresponds to on the horizontal axis. Well, 2010, that's 15 years since 1995. So we're over here. And then let's project that to our linear model. Let's find the corresponding point. And what is its y-coordinate? It's about 79. So this tells us that the mean ticket price in 2010 was approximately $79. And you can probably guess how we can answer the last question. We need to estimate in which year the mean ticket price was $65. In this case, we do have the price, but we need to find year. So we're gonna start on the vertical axis, the one that describes the prices. This time we have to simply find 65 on that number line. Here it is. Project that to the linear model and then see what's the corresponding x-coordinate. So it's about 11.2. So let's just say 11, right? Since this represents the number of years since 1995, which is going to round down. Okay, well, if this is 11 years since 1995, so the mean ticket price of $65 was in the year 2006, which is 1995 plus 11. So as you can see, having that linear model in front of us makes it pretty easy to make estimations and predictions. But since these are all estimations, we understand that we're making some hopefully small error every time when we produce that estimation. So let's talk about errors. Here are our scatter diagram and linear model once again. And when we look at this picture, which are the accurate descriptions of an authentic station? So which are the accurate or true mean ticket prices? So the true or accurate mean ticket prices will be the one that correspond to the data points because we plot them based on the actual data values. But which descriptions may or may not be accurate? These are all points on a model. And the error in the estimation is simply the difference between the actual value, the true value of a variable, and the estimated value. But in statistics, that error has a fancy name. It's called a residual. As we think about this a little bit further, we actually realize that there can be two types of errors. In some cases, we can underestimate when our estimation is below the actual data value. And of course, in some cases, we can overestimate. That's when our estimation is higher than the actual value. But just remember that when you compute a residual, and we'll need to do that in future topics, you always follow the same order. You take the observed value, so that's the actual value from the data set, and you subtract the predicted or estimated value obtained from a linear model. And as we talk about errors and estimations, it would be logical to conclude that some linear models might create more errors than others. So the question would be, how do we find a good linear model? Or not even good, but the best linear model that minimizes the amount of errors that we make when we use it? And that takes us to, well, the most important part of this topic, where we talk about how to find the best linear model that's out there for the given data set. Let's use this example. Here we have a table that describes projected population in millions of females under the age of 18. And this is how the scatter diagram or scatter plot looks like for this bivariate data set. Let's try to approximate linear model. Here are a few suggestions for you. What do you think about this line? Does it fit this data set, or you think you can find a better model? I think we all can see that this is not the best fit. How about this one? Wow, this is a much better fit. Well, in this case, we can see the difference between the two and right away say which one is better. A lot of times, lines can be very close to each other and differ by just a small degree of an angle, and one is still going to be better than the other. And the difference we won't be able really to detect by looking at the lines. So we need a better, or I should say scientific way to determine a good linear model. And we do have one. This is how idea of that method goes. So what we do is we find the vertical distances between the data value and the predicted value from the model. So it's observed value minus predicted value. So that's that residual that we talked about. So we find residuals or errors in estimation for each data point, for each linear model. And then for easier comparison, we want to add them up. But since some of them are going to be positive values and some of them are going to be negative and they can start canceling each other out, what we do, we want to square them first. So we find those vertical distances, we square them. This ensures that all numbers become positive, and then we add them. And the idea here is that we want to find the line for which the sum of squared residuals is a minimum, and that line will be used as a linear model. It's called the least squares regression line. Let's look at the formal definition of this line. Here it is. The least squares regression line, or simply the best fit line, is the line that minimizes the sum of the squared errors, or residuals. This line minimizes the sum of the squared vertical distances between the observed values of y, which is the response variable, and those predicted by the line, y hat. And this is something new that I haven't mentioned yet, so I'd like to emphasize this part. So the observed values of the response variable are denoted by y, we already know that, and the predicted values of the response variable are denoted by y hat. Now we have this overall idea of how the least squares regression line is found, but you can probably see that it's going to be very, very hard to test many lines by hand to find the least squares regression line. So we should have better and quicker ways of finding the least squares regression line. And the good news is that yes, we do have shortcuts. But before I show you those methods, I would like to note that when we say that we need to find the least squares regression line, we're actually going to find its equation first. You may remember from algebra that lines, straight lines, are described by linear equations. So our goal will be to find that equation, and then once we have the equation, we can always grab the line itself. So first, let's talk about how to find an equation that describes linearly related data by using a formula. First of all, this is the shape of that equation. Once again, you may recognize it from algebra. It has the form of a linear equation. In algebra, a lot of times we say y equals mx plus b. So in this equation, y, or I should say y hat, since it's used to predict values, and x are the variables, but b0 and b1 will be the numbers that we need to find. And these are the formulas that must be used to find b0 and b1. As you look at them closely, you're going to recognize all components of each formula. R is the correlation coefficient for the data set, and we already know how to find it. S sub y and S sub x, these are standard deviation for values of the response variable and explanatory variable. That will give us b1, that's the number that stands in front of x. And you also might remember from algebra that this number is called the slope. Slope is the value that measures the steepness of a line. And then to find b0, b sub 0, you have to use b1 that you supposed to find by then, and y bar, x bar, well, that's the notation for sample mean. So you have to compute sample mean for the values of the explanatory variable and response variable. So that's how you find this value that has also a special meaning. This is the y-intercept of the least squares regression line, or I should say of any line. The y-intercept is the value on the y-axis or on the vertical axis where a line crosses it. So as you can see, it's not that hard to find the equation of the least squares regression line by hand if you know the mean and standard deviation for both explanatory and response variables. I'd like to note that the equation of the least squares regression line, sometimes in short called a regression equation. And while it's not that hard to find that equation by hand, we're going to learn how to find it using calculator because it's going to be even quicker. This is how we find the regression equation using the TI calculator. We start by entering the data in our calculator. For that, you press on Stat, you go into Edit menu, so I press Enter. And since I have some old data here, I have to clear that, so I highlight L1, I press Clear and Enter. Then L2, Clear and Enter. Now I'm going to enter data given in the table. Step 1 is done. Now we're going to go to step 2, where we're going to find the actual regression equation. This is how quickly it's done using calculator. I'm going to press on Stat again, switch to Calc tab, and then go down to line number 4. Now that line, or the name of the menu item, might start making sense. It says lin reg. Well, it stands for linear regression. And that's where we're going to find the equation. So I press Enter. I confirm that my data is in list 1 and 2. I go down to Calculate, press Enter, and here where I have it. So let's look at what it says here. So first of all, the first line says y equals ax plus b. Do you recognize the form of a linear equation? So a represents the number in front of x, and that's the same as the slope. Well, here it is. It's given to us. It says that a is 0.155. And then b, the value that represents the y-intercept, is written over here. Here it is. It's 34.2777. So these are the numbers that we're going to place sort of a and b, and that will create linear regression equation. Let's talk about the rounding. Let's say we're going to round to 2 decimal places. Then a becomes 0.16 and b becomes 34.28. So this is the regression equation that corresponds to a linear model that describes the given example. So this equation can be used to graph the linear model, the line, or the equation itself can be used to do estimations and predictions. We're going to see all that in the next video.